Oh. Dude, no, series worksheet, so we're gonna get that.
We're gonna do the series worksheet today. Nothing on web work? Everybody's caught up on web work?
I actually do have a question on the web work. We gotta pull it up first.
Okay.
Could you go through the, or on number 7 earlier when I was talking to you about that one right there, where we got it as diverges, I believe.
Yeah, I don't remember the problem.
Yeah, let me bring it up real quick. It was, yeah, diverges by the ratio test and everything right there. If I was using the AST on right there, would I just, I would take the original, like set right.
That's a positive term series, so you don't do the alternating series test. Once you, since it has no negative terms, there's nothing else to check.
So because it's
Once you show that it diverged, it just diverges. There's no conditional to it. Right? You only check for conditional convergence for alternating series. But all those terms are positive, so you're done. It just diverges.
Okay.
Yes, sir.
What was the rule? I remember the question. So like if a sequence converges, does the series converge or is it the other way around?
Oh, no. It doesn't.
Like, I was just confused.
You can't tell. A sequence converges if it has a limit. This number L can be anything. It could be 0, it could be 1, it could be E squared, right? It could be anything. A series converges if it passes one of the series tests.
I guess I was just confused because there's a problem where A sub n was the same, but one of them was a sequence in that series. But I wasn't getting the same value for where it converged.
Right. The one on the worksheet
Yeah.
had
The first two problems is,
that's right.
yeah.
So from the worksheet that I sent you, does anybody have a copy of that worksheet?
Uh-huh.
'Cause I got extras if you want some.
Yes, please.
Little DNA on there though. I have the first two problems here. One of them talks about a series, the second one is a sequence.
Oh, I have a question about that one.
Okay.
Okay, so it was the alternating series. Oh, wait.
Okay, you got an alternating series.
-5 to the k of the k squared.
And the question was, does this converge?
Yeah, it was just asking if it was convergent, absolutely, conditionally, or if it.
Okay, so I'm gonna write it like this. Because -5 to the k is the same as -1 times 5 to the k. And then the properties of exponents, I can do that.
Okay.
Then when you look at this term here, whether it's with the alternating part or without, what do you know about that term there?
It grows slower than 5.
So the whole thing goes to infinity,
Mhm.
no matter whether it's alternating or not. For a convergent series, we need the positive term to have a limit of 0 before we can proceed. If the positive term doesn't have a limit of 0, we're done. It's not absolutely convergent, it's not conditionally convergent. Okay, so this goes to infinity, so it's not absolutely convergent and it's not conditionally convergent, and that's by the test for divergence. If the general term doesn't go to zero without the alternating part, it's not going to converge in any way, shape, or form.
So whenever you do the alternating series test, it has to be -1. There can't be anything else in there.
No, because we had that one with the cosine in it, so I took that one off.
Right.
But, you know, if you have integer values of, like this makes an alternating series. As if k is 1, the cosine of pi is -1. If k is 2, the cosine of 2 pi is +1. So something like this will alternate, but you don't see the -1 explicitly. Okay. Okay, so let's go back to that series handout. And you're asked the same question here. You're asked, does the series starts at 0 to infinity, 4 to the k over 5 to the k converge? And if so, to what? So it's a series, so it's got to pass one of our series tests. But if you're asked what it converges to, then it better be a series that we know how to find what it converges to. Telescoping or geometric. This one's geometric, right? You can think of 4 to the k over 5 to the k is 4 over 5 all to the k. And so when k is 0, I get 1 plus 4/5 plus 4/5 all squared. So it's geometric. Geometric series. R is the 4/5. It's smaller than 1, so it converges. 2, the sum of A over 1 minus R. A is the first term, so it's 1 over 1 minus 4/5. So it's 1 over 1/5. This thing converges to 5. Okay, now, when we check on number 2, the sequence, does that converge? Then you're checking something totally different. You're not doing a series test, you're just taking a limit. If you get a value of this limit, that's what it converges to. You get a value of this limit. 0, because it's faster on the bottom than on top. So the answer is yes to 0. Okay? Now, we've had the ones where the sequence converged to something that wasn't 0. So if the sequence goes to something other than 0, the series has no chance of converging if it has the same term, right? The example that I'm thinking of was something like this. The sequence 1 plus 1 over k to the k converges to what? E to the first power. So the series 1 plus 1 over k to the k diverges by, what test am I using? The test for divergence. It doesn't have a general term that goes to 0. Okay? So it's going to have a general term that goes to 0 before you do a series test. So it might be worth your while to check whether the sequence converges before you check if the series converges. So that was the point of the first 2 problems. Just to reiterate that it's real easy to check if a sequence converges. Take a limit. A little bit more work, a whole chapter of tests to determine if a series converges. Okay? Okay, so moving down the sheet. Did anybody try problem number 3? Did you get that it diverges? What test did you use? Integral test is an easy one. Comparison test is an easy one. Right? Comparison test works real well if you got polynomial over polynomial, because all you do is throw away the constants and the lower powers. So I can do a real quick comparison test on problem number 3. Integral test works well too, right? That integrates as a logarithm. And you're going to have the log of 5x minus 3, and x is going to go to infinity, so the log follows and goes to infinity as well. So you can use an integral test. 4 over 5 times k minus 3 compares to the series 4 over 5k. What kind of series is 4 over 5k?
P series.
And it's a divergent p series, right? What's the statement of the direct comparison test when you're comparing something to divergent?
Bigger than divergent is divergent.
So is this bigger than that?
Yes.
It is, because it has less in the denominator. We have 5k minus 3 is smaller than 5k by 3. So when you flip it over, is bigger than 1 over 5k. And then when you multiply both sides by 4, that doesn't change the direction of the inequality. So we can use the direct comparison test and say that this diverges because bigger than divergent is divergent. But I'm glad that you used the integral test because I don't want you to blow that one off. You're really good at integrating now. If you see something that you can obviously integrate, that's a quick way to do a test as well. Okay? What did you tell me about number 4? Diverges because? Test for divergence. The power on top, both of those terms are in power greater than the denominator. So number 4 diverges by the test for divergence. When you're comparing the size, you're looking at the highest power here was k cubed. The highest power here is the natural log of k, so that does not have a limit of 0. Do you need any more detail than that? So we're talking about number 5 now. Boy, we're working through these. Anybody do this one? By what? With a direct comparison test? We can make a comparison series just by throwing away the 2 constants. So let's compare this to series k divided by k times 2 to the k. So I've thrown away 9, so this one has a smaller denominator, right? I've made the denominator smaller, and I added 1, so I made the numerator bigger, a smaller denominator, a bigger numerator. This is a bigger number, right? So I know that k minus 1 over k, 2 to the k plus 9 is smaller than our bk series. But if I cancel the k's, I recognize what kind of series that is. Anybody else recognize 1 over 2 to the k? Convergent geometric series. So this is the correct statement of the direct comparison test. Smaller than convergent is convergent. Smaller than convergent is convergent. How about number 6? Does number 6 just scream at you what test to use?
Root test.
The root test. You got a quantity to the kth power. All right, so in the root test, you take the kth root and then take the limit. And if your limit is smaller than one, it converges, bigger than one, it diverges. So all the kth root does is it kills that kth power. And you get k plus 4 over 3k minus 1. And what's that limit? And so our conclusion is, so it's convergent by our kth root test. Now this series is a positive term series. So you can even say it's absolutely convergent because it's already a positive term series. What did you do on number 7? What do you feel like doing on number 7? You suspect it's telescoping because you got some subtraction going on there. So in a telescoping series, we should be able to write a general formula for the nth partial sum. A starts at 3, so we need to do that when we do our nth partial sum. So let's verify that this is telescoping. Put a 3 in for k, and I get 1/12 minus 1/16. Now I'm putting a 4 in for k. I get 1 over 16 minus 1 over 20. Now I'm putting a 5 in for k. And I get 1 over 20 minus 1 over 24. So I can see the telescoping part. So I'm going to go stop out at the nth term. The nth term has 1 over 4n. That should be the lowercase n. Minus 1 over 4n plus 4. So I'm going to call that Sn. And I'm going to simplify it to get rid of the terms that I lose. And I lose everything but the first term and the last term. So I can simplify my sum of n terms as this difference. Make sure you know which parts are coming out, right? I can generate, if I swap places with these two, then the second term would be available and the second to last term. So write them out so you know which ones subtract out and which ones are left. Then take the limit, as in, because this is a sequence now, right? Sequence converges if it has a limit. And if the sequence of partial sums converge to a limit, so does the series. And so what did you get as the limit? 1/12. 1/12. And so you say this is a convergent because the sequence of partial sums converge. And they both converge to 1/12. If you say it's telescoping, that's fine too, I'll believe you. Okay, did anybody get to the back of this page yet? Let's try them together. Start with work the next 3 problems. I'll kind of walk around and look at what you're doing. Write them down in case you can't read them, or for the folks looking at the little camera. I'm going to try these next 3 problems. Number 8. I heard somebody say the right test. to the k over k times 2 to the k. Kind of hoping that as you're looking at them, you already have the intuition of whether I know what test to use. And you can almost smell out the ones that are going to diverge. Maybe. Seeing these powers here and here and a multiplication, I know what test I want to use for powers and multiplication. See, the plus sign here keeps me away from that test that I'm talking about there. Bless you. We get this thing finished up today, and then you guys go to the baseball game this weekend, right? So you don't have any calculus to do. And they're giving COVID vaccines at the baseball game. So go ahead and go up and jab your nose if you haven't done it already. It's a quickie. Yep. Yep. Okay. Correct. No, you can do a limit comparison. Or a test for average. Yes. Correct. Compare you to a divergent series. Okay, so now is yours bigger than divergent?
Oh,
okay. Is that divergence?
Yeah.
Yes.
Okay.
Like limit comparison, better direct comparison. This is what was wrong. You don't want to give it to the cause, you don't need to your sums. Okay, so you can't get the product. But you got the right idea. There's two ratios. Put it back to that. That's what the composite divergence stuff is. So use a ratio test, because it's a big house with big problem. Either one will work. If there's, you got a convergence series. Oh, I think it's really easy. Oh, I see. And so, is the series smaller? Is the series you got smaller than that? So get their own size to do the duplication. Very good. Very good. Sometimes it's not more thinking about. Comparisons, one.
And of course, that's one of the comments.
The ratio test here shows that this divergence this is that one, that one, that one, that one. So we're left with 3K over 2K plus 1. The limit is larger than 1. So it diverges. Okay, but the plus sign here keeps all that fun canceling from happening. So a ratio test isn't good, but a comparison test is good. Unless you can see already that it grows faster on top than it does on the bottom. You can see that the limit of this is not going to be 0. You can do a test for divergence. If you do a comparison test, keep the numerator, pick the most prominent term down here, which is 2 to the k. So you can do a comparison test. Do 3 to the k over 2 to the k, which is a divergent geometric series. I've made this one bigger, so my series is smaller than divergent, so I can't use that. I'll use a limit comparison test by taking the limit of my series over that series. So that I can cancel there, and that's about all I can cancel. Again, I can't cancel through addition, but then I can take the limit with what's left. That is a job. And these behave like expressions of the same power. If you have expressions of the same power and you limit to infinity, you just take the ratio of coefficients. So I take the 1. Any positive finite limit in the limit comparison test says both series do the same thing. And so I go back up here and see that my comparison series diverge. So we have divergence. Things that are added are usually good with a comparison test. So I hope you're trying a comparison test on number 10. You can't tell it's convergent by looking at it. Because that's not a test for convergence. It's a test for divergence, but it's not a test for convergence. It's good to have the impulse that you suspect it's going to converge, but you got to prove it using one of our named tests. It's not like the old Andy Griffith episode where Gomer was taking a true false test and he banged his hand on the desk and his index finger hurt more, it was true. His middle finger hurt more, it was false. No, it's not convergent or divergent. You give me one of the tests. I guess you didn't see that episode. You probably are going, who's Gomer?
You wanted to do some real comparison test here. You wouldn't be able to because this is going to be smaller.
Right, throw the four-way too, so we have a P series. Compare it to a P series. You don't want to keep the four, right? Throw the four-way, make a P series out of it, and then do a limit comparison test. You're trying to make the comparison series a basic series.
Right.
There's really no reason to keep the four. It doesn't affect the long-term behavior of this thing. So we're going to just compare this to keep the squared k on top and the k squared on the bottom. But once you simplify that, that becomes a P series. But that's 4 halves minus 1 half is k to the 3 halves down here. So there's a P series that I'm comparing it to converge or diverge. It's a convergent P series. So I took stuff out of the numerator and denominator. So maybe you do a limit comparison test. Any positive finite limit means they both do the same thing. Positive finite limit means they both do the same. And since we just threw away constants, I guess our limit's going to be 1. You have to multiply it out, you can kind of see. If I just leave it in this form, that limit's going to be 1, right? Because I'll have a square root of k squared, square root of k squared. I just left it in that form. And so both do the same. So our series converges. Yes, sir. You're on 12? 12 is sneakily hard. And 11 is tempting you to use the K through test, but it don't work. That's right. That's right. That's what you do with number 11, the test for divergence. As long as you're right, if you guess wrong, then I won't believe you. It doesn't kill you to do all the steps, right? Because what if I did this? What does that go to? Eat of something. Go eat of what? Right? Because I put all kinds of bojangles in there.
Are you going to give us something like that?
You're tempting me. This one goes to e to the 7th, right? Doesn't go to 0. So by the test for divergence, this thing diverges. not go to 0. It goes to e to the 7th. So it diverges by the test for divergence. Why do you think you couldn't do all the steps in computing the limit if I put all those other numbers in there? I bet you could do it. But you're lazy.
Gonna make us do it later.
But you're lazy. That's right. Just do it later. That'll be your big Friday night. Save it for your highlight of your Friday night. Tell your significant other, I can't come over yet. I'm taking the limit of this thing. You better get over here. All right, sum a is equal to 2 to infinity. This one looks so innocent. But you're I tried a whole bunch of different things on this. So I'm kind of curious what you would try. One thing jumps out at me. Integral test jumps out at me, and I know how students hate that. But every time I tried a comparison test, I never got the right result. I can compare it to the stuff, but I just never got the right result. To make one of my comparison tests for it.
You're saying you can't do the integral test?
You can do the integral test. The integral test is easy on this one. You do integral. So try the integral test. Some of you, when you're doing the integral test, just write the integral and then tell me converges or diverges. I want to see the actual integral computed. Don't just say there converges or diverges, whichever you think it does. Find me the antiderivative and show that the integral does or does not exist. And then make the statement, since the integral converges, then the series converges.
Do we have to switch it to X?
No, you don't have to. It just kind of get all screwy when I put K's in my integral sign. This is America. You can use whatever variable you want. You can use smiley faces there if you want to. See, a lot of times when I try to do a comparison test, I say the natural log of k is smaller than the square root of k. But if I tried that here, I can't get my limit to go in the right direction. I can't get a positive finite limit out of it. Your integral converge? You're integrating u to the negative 2 du, right? Natural log of x, so du takes care of the 1 over x. This becomes the integral of 3 times u to the negative 2 du. So that's u to the negative 1 over negative 1, and whoops, negative 3 over u. And so the first term is going to be 0, and the second term will be divided by log of 2. So then say that the integral converges. So the series does too.
Conversion by integral test.
or convergent by the integral test. Convergent by the integral test.
Is 8.7 just a review?
No, 8.7 is power series. So it's more. It's got 13 done already. What'd you do? K through test. Everything in here has a K power. K through test is really quick when you recognize when you can use it. Less than one, it converges. Since the K's on the bottom, we get a limit of 0, right? How quick the K through test is, takes longer to write than to do. All right, 14 here. Anybody got a suggestion on what to try? What if that 1 was gone? What do you got?
Integral.
Ooh, I don't want to integrate. You can, but that square root of K is, that'd be integration by parts. I want to stay away from that. This is a named series.
Oh, is it more likely?
Say it again?
Is it more likely?
No, because the log on top. It's supposed to be, but the P series with the log on top is called a Q log. It's a Q log series, right? This is not a Q log series. This is, so you're going to compare it to a Q log series. Compare it to the natural log of K over the square root of K. Q log series behaves like a P series. It converges with the same size power. The power down here on the K is the power that I'm talking about. That's the Q. So here the power is a half. You think this is a convergent or divergent Q log? Divergent. Power on the P series or the power on the Q log is smaller than 1. It diverges. So you can do probably, I don't know, this is bigger than divergent, isn't it? Given series is bigger than a divergent series because the numerator is bigger by 1 inside there. So you can use the direct comparison test. Bigger than divergent is divergent. The direct comparison test. And the comparison should give you the same thing. K power to factorial, do you know what to do with 15? Ratio test. Powers and factorial, just say ratio test right out loud. Make sure you do the steps correctly. Well, since 16 is the only one that had any negative terms to it, answer the question here whether it's absolutely convergent, conditionally convergent, or divergent.
Quick question. So you take the AK curve and you come to the value of the AK curve
Correct.
as a little bit severe, or do you treat it as its
You
own
treat it as
series?
a positive term series, and you want a positive term series better.
Gotcha. Okay. Thank you.
2k plus 1 factorial is 2k plus 1 times 2k, no, times 2k minus 1 times 2k minus 2. 2 doesn't disappear. But the 2k plus 3 factorial is what you want to write out. So 2k plus 3 times 2k plus 2, and then the big one and spread it out. And that is 2k plus 3. Right? You have 2 in here, and then add that 1, so it's 2k plus 3 factorial. No, not yet. You have to spread it out. Put it in between step and between cancel. Right, it's 2k plus 1 factorial divided by 2k plus 3 factorial.
Because you get distributed to me, so plus 1 plus 2k plus 2.
Oh, okay.
Replacing this with k plus 1. So when you do that, it simplifies to the factorial. Right? Not that. Factorial. You have a k plus 1 in there, and that's a k. You write it. You write it. Step I want you to put in. Here's where you are. And I'm going to write this as 2k plus 3 factorial. Okay. But 2k plus 3 factorial means 2k plus 3 times 2k plus 2 times 2k plus 1 factorial. So when you cancel here, this is what's left. Cancel here, and all you got is a 3 on top. two things multiplied together on the bottom. Okay. So you get 0, and in the ratio test, when the limit is smaller than 1, converges. Okay. All right, so when you're testing this for absolute convergence over here, because I've got plus signs, you don't want to do the general ratio test. You just want to test it in absolute value with one of your positive term series tests. So your first test this using one of your positive term series tests. Right? Absolute value that gets rid of all of the alternating parts and just leaves you a positive term series. And how would you test that one? A comparison test with the P series, 1 over 2 squared of K. You don't have to keep the 2 if you don't want to. If you just throw away the 2, then yours, you probably need to do a limit comparison, don't you? Do a limit comparison. So this diverges by the limit comparison test. Yeah. The series 1 over 2 squared of K, divergent P series. And the comparison test will give you a 1. Right, both do the same thing. So it's not absolutely convergent. Let's see, this one has more on the bottom. So this one is smaller than a divergent. Smaller than divergent is no conclusion. Smaller than convergent is convergent. But smaller than divergent goes the wrong way. So not absolutely convergent. So next you're going to check conditional convergence using the alternating series test. These steps show that the limit goes to 0 and that it is decreasing. The decreasing is a formality when there's just a K in the denominator and a constant in the numerator. So is the limit. Alternating series test. With the limit K goes to infinity. 1 over 2 squared of K plus 3. And check if it's decreasing. By checking if the AK plus first term gets smaller than the AK term. The limit does go to 0 because it only has a K on the bottom. The K plus first term makes the bottom larger. So it makes the overall fraction smaller. Right? This made this term larger, so a larger thing into 1 makes a smaller fraction than this. So it is conditionally convergent. Okay? So I didn't get to do anything on power series. No, you want to stay longer though, don't you? But it's time. It's time to kick your rear ends out of here. I'll stick around if you have web questions. I can answer those, but if you want to go, you may go. I don't know what time, what date I put on the due date for that power series stuff. So, and the when?
Yes, we have a good amount.
You have plenty of time,
Yeah.
so you can kind of goof off this weekend. If you want to get ahead, I got videos online from previous semesters on how to do the next stuff.
I got one.
Yes, sir.
So for alternating series, like let's just say it's like -1 to K over like something like 5 to the K. Or I mean K to the 5 or or K to the 1. So average of
Either one,
series.
no, all alternating series that are P series
Yeah,
converge
yeah, and
conditionally.
yeah, and I was wondering, like, how is that, like, how does that feature work, just like mathematically? Because when I visualize like a series that's shrinking down, the P series, if it's K to the first, it doesn't converge because it does it too slow.
Right, but look at an alternating series takes a value from here, and then it adds nearly the same thing that's a negative number. And so it can go a little bit slower.
Okay, because it cancels itself
It
out.
cancels out, that's right.
Okay.
So you're adding like this little zipper there. So the size of it doesn't matter as long as it's decreasing, they kind of cancel each other out.
Whereas if it's just a regular P series.
Then you still gotta worry about the height away from it, yes,
Yeah. All right, I got it.
yes, yes, sir.
Can you please briefly like refresh me on the Q-log series?
A Q-log is a series that has a logarithm on top and a K to the power on the bottom. Log to the first power on top and some sort of power on the bottom. And we showed with an integral test, which usually involved integrating by parts, that this is going to converge if Q is bigger than 1 and it diverges otherwise. Q less than or equal to 1. But you can show that with an integral test if you do forget it.
Has to be a log to the first power.
Has to be a log to the first power on top.
Ln squared.
Right, right.
If you have an ln to the power of whatever on the bottom, right?
No, if you have if it's a logarithm on the bottom, it's not a Q log anymore.
Wait, no, we did earlier.
But we did an integral test on it,
Oh, that's right.
right? Let me see what papers I got graded here.
Did you want to send web work for 5.5?
Did I do what to it?
Do you explicitly have